Dr. Kaushal Kumar Jha. Dr. Kaushal Kumar Jha is the principal investigator and founder of NoonRay Energy Private Limited. He consults various organizations in automotive, thermal, and energy management. Dr. Kaushal is Adjunct Professor in the Department of Engineering Design at IIT Madras. He is also the CEO of Center for Battery Engineering and Electric Vehicle at IIT Madras and the Center for Excellence in Energy and Telecommunication and R&D Society of IIT Madras. From an engineering background, Dr. Kaushal is Ph.D. from IIT Madras in Mechanical Engineering with more than a decade of experience in industrial and academic R&D. Mr. Kaushal will deliberate upon low GWP refrigerants in the mobility sector. Let's welcome Mr. Kaushal.
So let me move towards what I have taken. A topic is low GWP refrigerants in mobility sector, and I'm basically a thermal engineer. So refrigerant becomes a very special part in that case, especially when you are looking for maintaining a temperature around 25 degrees anywhere. In the condition where India, we have something like 51 degrees in Delhi, in Rajasthan. So from the first principle, what we say that you can reject the heat only from higher temperature to lower temperature. Wherever you have to go from lower temperature to higher temperature, you have to do some work. Now, it can be done in different ways using the waste heat or something like that, using in vapor absorption system. But in vapor compression system, what you have to utilize is a power to compress the refrigerant, go to the next level, change the phase, reject the heat to the ambient, whatever excess heat is there, come back through expansion valve, reach to the evaporator, take out the heat wherever you require to take, either it is an electric vehicle as a battery or the cabin, and keep doing this cycle. So that's what my second slide is about. The compressor is what increases, because before understanding the refrigerant, we have to understand how it works at all. So the compressor increases the pressure and temperature of the refrigerant because you are looking for the lower temperature to higher temperature, and heat transfer cannot happen unless it is at higher temperature. So we push the refrigerant to reach it to the condensing pressure and subsequently at the higher temperature also. And then it is able to reject the heat to the ambient, whatever excess heat what we have taken on other side, changes its phase from vapor to the liquid in the condenser while doing that. And the same time, again, it changes in the phase in evaporator where it takes heat out. It absorbs the heat from liquid to vapor cases. So that's overall about the refrigeration cycle and vapor compression cycle, basically. Now, we have to understand refrigerant, ODP and GWP, which you have already nicely explained during the panel discussion. What we want: low ODP, low GWP, non-toxic, non-flammable, miscible with the lubricant, because the problem is that something which is compressing is a moving part. Refrigerant does not require lubrication, but that moving parts require lubrication, and that lubrication has to go through the running fluid only. The problem is that as soon as we put the lubricant, my thermal properties change it, and so my heat transfer efficiency. So that's one of the important part, but that has to go into the refrigerant to make the moving part working for more time. Then we have something like we say direct expansion devices. That's what vapor compression system, and that is being used in air conditioning as well as in heat pump. Now, defining GWP, a comparative number to the mass of CO2, there is nothing like zero GWP. Where I have not heard zero GWP. The GWP is always considered CO2 as a reference. Theoretically, or by us, we can say, okay, water and other things, but even we talk about hydrocarbons, they have much more GWP than the CO2. So CO2 is a reference point itself is like we have some reference, and that's where we start pulling that the CO2 is one. So if we consider something like R134A, as other panelists say, 1300, so what we have put is approximately 1430 over 100 years cycle. The leak of a ton of refrigerant is equivalent to emitting 1430 tons of carbon dioxide. And that's how we say it's CO2 is one and others compared over that one. So what happens, since this is leading to the heating of the planet, so finally global warming, every year we are getting increase in 0.1 degree, 0.01 degree temperature. And over the year, being an automobile engineer, automobile thermal engineer, 10 years back, we used to take the worst condition as 45 degree ambient, but for designing our system. But today we are taking 51 degree centigrade as our design parameter for worst condition. In that 10 to 15 years itself, we have reached to 6 degree extra. Now, not only that, if you look upon mobility sector, 10 years back, we had a couple of cars where we had AC. Now every car comes with the AC, air conditioning system. So we have that thing. So we have to really start worrying about if anything leaks, there is a problem. The another problem is that on the mobility sector, we have to look upon all the vibrations and everything. So wherever we have a refrigerant, we go many of the times with a rubber pipe or EPDM pipe at some of the position, not whole metallic. So there is always a possibility that some of the molecules of the refrigerant will escape from that. And in a year or two, we do some top up. That generally is getting avoided in the industrial or wherever we have a static system, because we have all metal pipe from that refrigerant cannot leak unless we allow them to leak. But in the automobile sector, what you have, some of the pipes are already made of EPDM and flexible material, and there is always a possibility that some of the molecules over the time will escape from that one. So looking all the things, if you look upon the refrigerant property, that also we have discussed higher flammability, lower flammability, no propagation numbers, A1, A2, B1, B2 categories and other things. But in automotive sector, it's very stagnant. You cannot have GWP now more than 150. It cannot be flammable. It cannot be toxic. It has to be odorless. And looking all those aspects, if you look upon, and what we are using right now is R134A, which has a GWP of 1400 or 1500. So what we are using, I cannot change immediately from the existing vehicle, but the new vehicle has to go with something which is already proven. So no flammability makes all hydrocarbon no go in mobility sector. So the only option comes HFO. And that HFO 1234YF, that's only one option is available today. Problem is that HFO 1234YF has all the patents only with the two companies, DuPont and Honeywell, and they have made the pricing so high that it cannot be adopted. They can say R&D cost and other things. If you look upon our Prime Minister a couple of days back thing, you cannot profit from a technology which is of use for the global warming, for the climate change. So unless that things has not been cleared out by the people or by the companies like DuPont, Honeywell, even though you have put a lot of R&D, but you have to also look upon the society. It's not only we are going to impact it, you will also be. So look upon on that perspective so that it can be used more easily, more accessible to all the people, including the cost wise. So that's only one option. The second option, what we get, if you look upon the regulation. So in 2000, if you see Europe, now they don't have any other option than using the R1234YF and CO2. That's only two options they have in the mobility sector. In US, from 2021, it's banned. Anything other than the R1234 means obviously it comes only that option. R134A is banned, so you cannot have anything other than the CO2 and CO2 is not a developed system till now. India, they are looking for 2030. They said no, I cannot go along with you, because our market is different, our costing is different. I'll take some more time to go out with. But having said all those things, what we are doing, can we look upon something? Can we relax on the flammability side? Hydrocarbons are really a good refrigerant, natural refrigerant, much better performance. Another problem is with R1234YF is that if you look upon the heat transfer efficiency, overall heat transfer efficiency, it's a 10% lower than R34A. So what another panelist was saying that, okay, you have to also look upon overall energy consumption. Obviously, that is going to increase. People has found a way, like we'll use internal heat exchanger and blah, blah. We can still remove more heat or equivalent heat than R134A, but still it's going to add the cost there by adding some other subsystem. And that subsystem, I can still add in R134 also to make it more efficient. So having said all those things, what I see, okay, R134YF is an option right now. Obviously a costly option, but in the future, we have to look upon something on CO2. We say it's a number as R744. It takes new development, and being 1.5 billion people country, I'm sure we all can do it together and much more efficient system and natural system. So with that, I'll stop my presentation because the rest of the thing is all about refrigerant.